So next we have some notations that you need to know for comparing sample statistics and population parameters. So when we're looking at the mean, the notation for population is your mu, that's your notation for population mean. And then your x bar is for sample mean. So population mean is your mu, and then sample mean is your x bar. For variance, we have sigma square for populations, and then for sample variance, we have s square. And then for standard deviation, we have sigma for population, and then s for sample standard deviations. So that's the notation difference between population and sample. The next topic is empirical rule. We have the 68, 95, and 99.7%. And the empirical rule approximate the variation of data in the normal distributions. So we have a bell curve distributions. So in the diagram here, we have a bell curve. And the bell curve means that we have symmetric on both sides, left side and right side, they are both symmetric. And on the x-axis, we have the x value, and then we have the mean here in the middle. And what the empirical rule states is that if we take the mean, and then we plus minus one standard deviation, so the green area here, then we get 68% of the data set. And the 68% of the data set is your area under the curve. So this green area here, the area under the curve, represent the probability, which is your 68% of the data set. And that's what the empirical rule states for the 68. 68% represent, we have the mean plus minus one standard deviation. So we have the mean, and then we plus one standard deviation, and then we minus one standard deviation. So that gap here, that gap, the area of this gap here, contains 68% of the data set. And then same idea for the 95%. 95%, we have the mean plus minus two standard deviations. So we take the mean, and then we add two standard deviations, and then we minus two standard deviations. So this whole area here, so the green area and the blue area, so that whole area here, that's your mean plus minus two standard deviations. And that whole area here is 95% of your data set. It contains 95% of the data. So your mean plus minus two standard deviation is 95% of the data set. And then last one is your 99.7%. So for 99.7%, we have the mean plus minus three standard deviations. So we have the mean plus three standard deviation and then minus three standard deviations. So the gap from mean minus three standard deviation to mean plus three standard deviation, that gap here contains 99.7% of your data set. So the green, blue, and purple, so these area here all add up to 99.7% of your data set. And that's what the empirical rule 68, 95, 99.7% represent. 68 represent mean plus minus one standard deviations. So if we take the mean plus minus one standard deviations, we have 68% of the data. If we take mean plus minus two standard deviations, then we have 95% of the data set. So the area under the curve for mean plus minus two standard deviation is 95%. Last one is the mean plus minus three standard deviations. We have 99.7%. And that's what the empirical rule tells us for normal distribution bell curve. So now that we know how to describe one numerical variable, so next we're going to look at describing the relationship between two numerical variables. And what we're going to look at is covariance and coefficient of correlations. So covariance measures the strength of the linear relationship between two numerical variables. And then similarly, correlations measures the relative strength of the linear relationship between two numerical variables. So the major difference between covariance and correlation is that for covariance, there's a major flaw is that it is not possible to determine the relative strength of a relationship from the size of covariance. Because for covariance, there's no boundary. All we know is that if the covariance is greater than 0, then we have the same directions. If the covariance is less than 0, then we have opposite directions. And then if the covariance equals to 0, then they're independent. So that's all we know. As for correlations, it tells you the relative strengths. And how it tells you the relative strength is that it is bounded between -1 and 1. So the closer it is to -1, then that means the stronger we have the negative linear relationship. The closer it is to 1, that means we have the stronger the positive linear relationship. The closer to 0, that means we have a weak relationship. And again, the reason why correlation can tell us the relative strength is because correlation is bounded between -1 and 1. So we're going to go through example 2, and I'll show you how to calculate covariance and correlations. So example 2, the following data represent the calorie and sugar in grams of various breakfast cereal. Use the data provided to complete part A and part B. So in the data set here, we have the different types of product of cereal, and then we have calories and sugars for each type of product. And what we're asked to do is calculate the covariance and correlations. So when we look at the data, we know that these are two different types of numerical variables. So in column C, we have the calories, and these are all numbers. And then in column D, we have sugars, and these are all numbers as well. So we have two numerical variables. And right now, I'll show you how to calculate the covariance and correlations. Algebraically, we have the formula here for covariance and correlations. So right now, I'm just going to show you the quick and easy way, the Excel formula to calculate covariance and correlations. So for covariance, when we're looking at the covariance for between sugars and calories, the formula that we're going to use is covariance dot S for sample. If it's dot P, then it's population. If it's dot S, it's for sample. So right now, these are just sample data set. So therefore, we're using the covariance dot S. And then it will ask you for the array 1. Array 1 is your calories. So calorie, we're going to highlight the data from C12 to C18, comma, and then it will ask you for array 2. Array 2 is your sugar. So sugar is your D12 all the way to D18. And then we press enter, and this will give you the covariance. So covariance.s, and then we highlight the first data set calories, and then we highlight the second data set sugars. Next, we have the correlations. Correlation, we're going to use the formula CORREL, correlations. That's the formula that we're going to use in Excel. And then same structure, it will ask you for array 1. Array 1 is your calories, so highlight the data from C12 to C18, comma, array 2 is sugar, so D12 to D18, and then enter. And then it will give you the correlation number, which is the 0.76. So when we look at covariance, we don't know if this is strong or weak, because covariance just tells you a number and then there's nothing to compare to. But for correlation, it tells you the relative strengths, because correlation is bounded by -1 and 1. And for correlations, the rule is that if our correlation is greater than or equal to 0.6, then we have a fairly strong relationship. So in our example, we have the 76%. So what that means is that we have a strong relationship between calorie and sugars. And that's what the correlation tells us. We have a strong positive linear relationship between calorie and sugar. And that's example 2.